Inviting me. Okay, so I'm going to assume that most people are familiar with deep learning and kind of the so-called revolution that's happened in AI over the past decade or so. It's exemplified by, of course, results on the ImageNet Object Recognition Challenge, which was a contest that took place every year for about 8 years. And this is the error rate on object recognition on 500,000 images after training on over 1 million. And you can see that this is an approximation of human performance on this. And in 2012, we got the first deep neural networks being applied to this challenge. And as the years went by and the networks got deeper and deeper, the error rate kept going down and down until it was below this 0.05 line. And then we got headlines that said things like, computers are now better than humans at recognizing and sorting images, which actually was not true, but because this was just a particular data set. But this kind of headline is common in the field, that a particular benchmark is then identified with a whole kind of general task. And then, we get things like Google's AI can now caption images almost as well as humans. And all of these kind of add up to thoughts about self-driving cars, since these vision algorithms and other algorithms are so successful that it's been predicted that things like self-driving cars will be here any day now. Of course, this was 2020, so that didn't happen. Here's what one AI researcher said about this. Suppose expectations are too high, and this will eventually result in disaster. Suppose 5 years from now, funding collapses as autonomous vehicles fail to roll, et cetera, et cetera. You can't get money for anything connected with AI. Everybody hurriedly changes the names of their research projects to something else. This condition is called the AI winter. Well, of course, this was said in 1984 by Drew McDermott, AI researcher of that time, and yet it could be repeated now, that these kinds of cyclical periods of very high optimism for AI, followed by disappointment, or sort of followed by exaggerated claims, followed by disappointment, followed by the AI winter, seems to happen every so many years. In the 1990s, when I first got my PhD, I was advised not to use the term artificial intelligence on my job applications because we were in an AI winter. So this is actually true. This happens. But the kind of optimistic predictions that we've been getting lately really started as early as the field started. Claude Shannon, for example, predicted that in 1961, that within 10 or 15 years, we get something like the robots of science fiction fame. In 1965, Herbert Simon, one of the pioneers of AI, predicted that within 20 years, machines would be capable of doing any work that a man can do. Note the sexist language of the 60s. A few years later, Marvin Minsky, founder of the MIT AI lab, predicted that within a generation, say 20, 25 years, the problem of creating AI will be substantially solved. Well, of course, none of those came true. And much later, John McCarthy, another pioneer of AI, said, well, the problem was AI was harder than we thought. Well, the deep learning revolution has prompted many people to now think, well, maybe we've transcended this problem and AI has now become conceivable, sort of general human level AI. Shane Legg in 2008, co-founder of DeepMind, said that he predicted human level AI would be passed in the mid 2020s. Mark Zuckerberg, 2015, noted that Facebook, now called Meta, of course, one of the goals of the company for the next 5 to 10 years is to get better than human level at everything, including general cognition. And Stuart Russell, an AI researcher at Berkeley, in his latest book, asked, when will super intelligent AI arrive? And he predicted it would probably happen in the lifetime of his children, which is, he noted, is more conservative than that of many AI researchers. So are these people sort of optimistic for a good reason, or are we just seeing another repeat of the extreme optimism followed by a near-term AI winter? Well, I think we're starting to see now some of the important limitations of the current AI spring, if you will, of deep learning. Some of them include what people call shortcut learning, where the system learns some kind of statistical correlations that are associated with correct answers on a task, but it doesn't actually learn to do the task in any general way. We see adversarial vulnerability, where deep learning systems are vulnerable to engineered changes in the data that wouldn't affect a human, and more generally, a lack of common sense. So let me tell you about a few of those. Shortcut learning, well, here's a really simple example. One of my PhD students did this project where he tried to train a deep neural network to recognize photos with animals versus photos without animals. And he trained it on a large set of nature photographs like these, and its performance was quite good. It was able to detect photos that had animals versus no animals with high accuracy. But when he actually tried to look under the hood to see what features of the image, what pixels were involved in the decision, he found that often the system would focus on the background, not the animal. And one of the things that it had learned is that blurry backgrounds are associated with animal photos because the photographer is focusing on the animal, whereas the non-animal photos were all these kinds of landscape photos without a blurry background. So that was a shortcut that allowed the system to do well on the task without actually learning what an animal is. And this kind of shortcut is seen all over machine learning. You know, recently, one group did an experiment where they took a deep neural network that had learned to recognize images like a school bus with 100% confidence, okay? But if they photoshopped that object into unusual poses, the neural network was very certain that it was a garbage truck or a punching bag, 100% confident, or a snowplow, okay? And so that's really showing that the system is focusing on features that are very different than the kinds of features humans use to recognize objects. You know, there's some features of these images that it's zeroing in on to make it extremely confident of these incorrect classifications. And they showed this with, say, fire trucks also. And, you know, the lack of ability to recognize objects robustly can lead to things like crashes where Tesla on autopilot can crash into a stopped fire truck on the road. So there's a lot of people who are interested in this idea of shortcut learning, and in particular in high stakes cases like for medical diagnosis. And some people have compared machine learning systems with Clever Hans, the famous horse that back in the 19th century was able to supposedly do arithmetic, you know, would be able to tap out its hoofs to give the answer to any arithmetic problem. But it turned out that Clever Hans was actually responding to very subtle body language from its trainer. And this analogy is that in some cases, machine learning systems have become a kind of Clever Hans, where they're responding to subtle statistical associations in the data, but they aren't actually learning the task that the humans are hoping that they would learn. Adversarial vulnerability is something that you all have seen, I'm sure, with starting with this paper, which from 2013, which was titled "Intriguing Properties of Neural Networks," which is a mild way of putting it, that the discovery that you could engineer small modifications to an image. This is sort of the highly magnified noise engineered noise that you're going to add to this school bus image and cause a neural network, which previously had been correct, to, on these new versions of the image, which look identical to humans as the original, to cause the neural network to classify it as an ostrich in all cases. And these kinds of attacks have been shown to work not just for images, like the ones I showed in the previous slide, but for things like facial recognition, where you can have special eyeglass frames with patterns that fool a facial recognition system into identifying, say, this author of the paper with as the actress Mila Jovovich. And in the physical world, being able to put stickers on stop signs that cause a vision system for a self-driving car to perceive these as speed limit 80 signs. So these are all attacks that have been sort of described in the literature by machine learning researchers who are trying to show vulnerabilities of these systems. So these people showed that this would be fairly robust across different angles and distances of view. Perhaps the most broad limitation of today's AI systems are the lack of understanding and common sense. So I learned that the most common accident for self-driving cars, either the Tesla autopilot or the experimental vehicles that we're seeing on the roads, is that humans rear end them. And the reason for that is that these cars tend to stop unexpectedly. They slam on the brakes for no reason that any human could see. And so the humans, who are not very good at paying attention, are following too close behind them and rear end them. And the reason that they stop so suddenly is because it's hard to figure out what is worth stopping for. Should they stop for a floating plastic bag, or here in the Southwest, we see this kind of thing, a tumbleweed. Would a car that had not been trained explicitly on this kind of image be able to figure out that it's okay to drive through a tumbleweed, or to know, for instance, that a flock of birds is very likely going to fly away, or that maybe you shouldn't drive through a pile of glass on the road, or that this snowman is not going to dart across the road in front of your car. So all of these things might be called common sense, new situations that humans know how to deal with because they know how the world works. Here's an interesting example of a lack of human common sense. This is showing what a self-driving car's camera classifies different things as. And these are bicycles on the back of, painted on the back of a car. And yet the self-driving car doesn't distinguish them from real bicycles. And this was something that appeared in Twitter. Someone driving a Tesla on autopilot found that their car would just slam on the brakes at this point on the road. And they couldn't figure out why until they suddenly noticed that there was a billboard of a sheriff holding a stop sign. And the car thought that was a real stop sign. So this kind of gap between humans and machines on sort of common sense, figuring out the world and what they should be stopped for in a car is turns out to be one of the oldest and hardest problems in AI. Oren Etzioni, the head of the Allen Institute for AI, called common sense the dark matter of artificial intelligence, saying that like dark matter in the universe, common sense is all around us. It's what we're constantly doing, and yet we're unaware of it. And we don't know how to define it very well. So it's something that a lot of people in the field are putting a lot of effort into trying to get computers to have common sense. Paul Allen, co-founder of Microsoft, before he died a few years ago, he started his own institute in Seattle to study common sense in machines. And the Department of Defense in the US is putting a lot of money into trying to give common sense to machines. And in fact, this particular project, one part of it is a grand challenge to build a machine and train it to have the common sense of an 18-month-old baby, with the appropriate developmental milestones along the way. So it's kind of the paradox of AI that, we have machines that can outperform humans in so many ways, on playing chess or Go, on translating from hundreds of languages, on all kinds of things. And yet it's still a grand challenge to have the common sense of an 18-month-old. So I was interested in this question of why people in AI and who cover AI in the media, for example, tend to be more optimistic perhaps than is warranted. So I wrote this paper called "Why AI is Harder Than We Think," and got a lot of both positive and negative comments on it. And I'll share some of those with you a little bit later. But what I did in the paper was I said that there were some fallacies that all of us kind of fall in when thinking about AI. And those fallacies tend to make people more optimistic, perhaps, than they should be. So the first fallacy is that narrow AI is on a continuum with general AI. So this is the idea that once we've made progress in one area, that's actually progress towards more general intelligence. So IBM, back when it was promoting Watson, which you may remember as a healthcare assistant, said that Watson was a first step into cognitive systems, which is their term for general AI. So this idea of a first step, okay? Or AlphaZero, the program that was able to learn to play chess and Go, was called a first step in creating real AI. GPT-2 was seen as a step towards general intelligence. So this whole idea, this image of, we're just taking these steps on this continuum towards general AI. Well, this was a long time ago called the first step fallacy by the philosopher Hubert Dreyfus. He characterized it as the fallacy that we've been inching along a continuum, at the end of which is AI or general AI, so that any improvement, no matter how trivial, counts as progress. And he said, no, there's in fact a discontinuity in this assumed continuum of steady incremental progress, and it's the common sense knowledge problem. So, this has been a problem for a long time. But if we see progress, like, just the last couple of weeks, we saw in the news, we saw this incredible program that's able to take a sentence and generate an image. Like if you say, 6 nuns eating a pizza, it can generate a picture of that. And a lot of people said, oh, no, we must be really close to general AI. So that might be called one of an instance of the first step fallacy. Dreyfus's brother, Stuart Dreyfus, made the analogy that it's like claiming that the first monkey that climbed a tree was making progress towards landing on the moon. Whereas, it may be that in order to make real progress, we have to climb down the tree and build a rocket ship. The second fallacy is that easy things are easy and hard things are hard. So that the idea that things that we consider easy, we humans consider very easy, we assume often will be easy for computers, and vice versa. So Herbert Simon said a long time ago that everything of interest in cognition happens above the 100 millisecond level, the time it takes to recognize your mother. So sort of dismissing all the kind of very unconscious perceptual processes. And more recently, the deep learning pioneer, Andrew Ng, said almost the same thing. He said, if a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI either now or in the near future. So the idea that, all these things that happen in this very quick, unconscious level that are so immediate for us are also going to be easy for AI. And a little bit more subtly, Demis Hassabis, the co-founder of DeepMind, and colleagues wrote in their paper about AlphaGo that Go is one of the most challenging of domains. Okay, and it has been a grand challenge for AI for decades. But to say that it's one of the most challenging of domains, we have to ask, challenging for whom? Certainly challenging for people, but is it more challenging for computers than, say, as the psychologist Gary Marcus pointed out, the game of charades? Any 6-year-old can play charades very well, and yet the kind of linguistic capabilities and ability to gesturing and theory of mind that is required to play charades exceeds the ability of any system, AI system, that we've ever seen. So Go is hard for humans, harder than charades, but it's not harder for machines. So this fallacy that if Go is one of the most challenging of domains and computers can now play Go better than humans, we must have conquered the most intellectually challenging of domains, for machines as well. So this Moravec's paradox, which has been around for a while in AI due to Hans Moravec, said it's comparatively easy to make computers exhibit adult level performance when playing on intelligence tests or playing checkers, which, now we would say playing chess or Go, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. And to add the Department of Defense, DARPA common sense grand challenge, we can add common sense to that. Marvin Minsky, who made such a grandiose prediction for AI early on, said later that the problem is, in general, we're least aware of what our minds do best. So we assume that what our minds are really good at, like walking around a room without bumping into anything, or having a conversation, or describing a visual scene, etc., those things seem very easy to us. So it's been assumed that those things will not be so hard for machines. My third fallacy was what I called the lure of wishful mnemonics. So I got this phrase from Drew McDermott, who wrote in 1976 about the idea of wishful mnemonics. And that was his term for sort of anthropomorphizing what machines do. He was complaining about back and then, people would call the main loop of their programs understand and then assume that they understood. And he said many instructive examples of wishful mnemonics by AI researchers come to mind once you see the point. Well, it turns out that there's a lot of modern examples of wishful mnemonics. So, another example from IBM, one of their blog posts about Watson said, Watson can read all of the healthcare texts in the world in seconds. And I've heard statements like that about, the latest programs like GPT-3 and other language models saying, they've read all of Wikipedia and so on, where this word read, you might call that a wishful mnemonic. It carries all of the overtones of what humans do when they read. That is, they actually understand what they read. And, they bring to bear quite a bit of world knowledge about that and have models mental models of things they read about. Whereas Watson and GPT-3 are doing something very different with the text that they process. But if we think that they're reading, then we might consider them to be more intelligent than they actually are. And, this you can just go on and on with this, understanding these terms, even subtle terms like goals. AlphaGo's goal is to beat the best human players, not just to mimic them. Well, does a program have a goal in any sense, like what a human has? Not really, but it makes it sound like that we should be giving this system a little more intentionality than it deserves. We also call our benchmark data sets in machine learning things like reading comprehension or common sense understanding or the general language understanding evaluation. These are all actual names of benchmarks. So when machines do end up doing better on them than humans, which they have on all of these benchmarks, it can often be mistaken that they've then surpassed humans on the general task, which is not the case at all, because often these benchmarks don't actually test what their name implies. And even more kind of fundamentally, we call our methods deep learning or neural networks, where learning, has a certain sense for when, say, humans learn, which almost always implies that they can apply what they learned to new situations, which is rarely the case for deep learning. And, neural networks are not they're only very loosely neural. And yet these terms can mislead people into thinking that these are more human-like than they really are. And my last example is I've seen a lot of over-attributions in descriptions of what machines have learned. So here's just one example that I found really striking. So one of the things that DeepMind did before they created AlphaGo was they built these deep reinforcement learning systems to play Atari video games like Breakout. So Breakout's a game where you move this paddle horizontally and it hits a ball, and the ball, when it collides with a brick, the brick explodes. And so the goal is to get the highest bricks here. And so here's what DeepMind wrote. They said, after 600 episodes, the DeepQ network finds and exploits the optimal strategy in this game, which is to make a tunnel around the side like this, and then allow the ball to hit the blocks by bouncing behind the wall. So look at these terms that they're using: tunnel, ball, blocks, wall. These are all human concepts, and indeed ways that we would think about playing this game, perhaps. But the DeepQ network only learned from the pixels of the video game. So it's not clear that that the system actually learned these more general concepts. And in fact, when another group did an experiment where they looked at a DeepQ network that had learned to play this standard Breakout and was able to use that optimal strategy, they said, can that system transfer its knowledge to a version of Breakout that has the paddle shifted up by a few pixels? Well, if it had learned these concepts like tunnel and block and ball and bricks and so on, it seems like it would have no problem because nothing's really changed except the height of the paddle. But it turns out that that system that learned on this version of Breakout couldn't play this version well at all. So it really hadn't learned those concepts that we were attributing to it. So the last fallacy, the one that I got the most kind of passionate pushback on, was that intelligence is all in the brain. This version of the brain in the vat. This is sort of a cartoon of AI, right? So we have these systems and neural nets in our software that are somehow getting inputs from the worlds that are getting pumped into them, and then they pump out outputs. There's no body. So this seems to be an implicit assumption of most work in AI. people talk about AI, how AI just needs the computational power of the human brain. And that when we get human brain scale AI, we'll be able to do all the tasks that the brain can do. And so you see headlines like this about talking about the compute power of the brain. And I heard this quote, I read this quote from Geoffrey Hinton, one of the, deep learning pioneers, where he said, to understand documents or language at a human level, we're probably going to need human level resources. We have trillions of connections in our brains, but the biggest networks we built so far only have billions of connections. So we're a few orders of magnitude off, but I'm sure the hardware people will fix that. Okay, so, this is this kind of idea is a source of optimism about, say, how soon we're going to get machines that can understand language. But of course, many people in cognitive science believe that the brain is not the only aspect of us that gives us intelligence, that the brain's deeply intertwined with the body and the social world and the cultural system we're embedded in, and that intelligence can't be separated from all of those things. So just to sum up, some of the open questions spurred by these fallacies. If narrow AI is not on a continuum with general AI, how can we assess progress toward general or human level AI? If easy things for humans are not easy for computers and vice versa, how do we assess the difficulty of a domain for AI? We can't just say, Go is the most challenging of domains, because, it really depends. Are you a human or a computer? How do we talk to ourselves about what machines can and can't do without fooling ourselves with the wishful mnemonics? And how embodied or socially, culturally embedded does intelligence need to be? I don't have the answers, but I think these are some of the most important questions that we need to be asking if we want to have a true sense of how close AI, the current state of AI is to general intelligence. So just recently, the last couple of weeks, we've seen two big so-called advances in AI. You may have seen this. There's this program called DALL-E that from OpenAI that you can give, I mentioned, you can give it a sentence and it will, a description, and it will draw an image of that. And another giant language model from Google called Palm that outperforms GPT-3 at lots of language tasks, can explain jokes and do all kinds of things. And so a lot of people started posting on social media about how close we were to human level AI, and these really show this progress really showed that. So I wrote this tweet where I said these were very impressive and awe-inspiring, and it seems to convince people that we're closer and closer to human level intelligence. And one of the cautions I said is, like, there have been these challenges on abstraction and analogy that have been around for ages. One of them is the Bongard problems, which I don't know how many of you are familiar with those, but they were proposed in the 1960s as a challenge for AI. The idea is that you have 6 boxes on one side, 6 boxes on another side. The other side, you can think of these as your training examples from 2 classes, and you have to express in some way the pattern that distinguishes the 2 classes. So here you would say, well, the 2 objects are the same and the 2 objects are different. It turns out that this notion of same versus different, being able to recognize that abstract concept that's so easy for us, still stymies all AI programs. There's many examples of Bongard problems, such as this one, which you have to sort of see an abstract numerosity, these are sort of abstract versions of 3 versus 4. And there's many, many examples like this. And I said, well, we see all these wonderful examples of AI being used to do like generate language, generate images, and yet why can't these systems solve these problems that have been around for the last 60 years? And I saw what I got back was quite a bit of optimism on AI. Christian Sajedi, who's a researcher at Google AI, said that he thought that a 500+ billion parameter transformer trained on multimodal web data could solve these problems even today. And by solve, I mean, you only get 6 examples of each class. And then he offered a public bet that such a demonstration would happen within 2 years using today's transformer architecture, exploiting few-shot generalization. Well, I don't know if this is going to happen, but I feel that we're still falling prey to a lot of these fallacies that we see, that I pointed out, and that this is another example of it. So I talk about this kind of thing quite a bit in my recent book. I'm happy to have a discussion about any of these issues and answer any questions. So thank you.
Thank you. So please ask your questions directly to Melanie, or like write them in the chat, and we can read them. But that would be better for everyone if you can just ask the questions directly to have more active discussion.
Or give me your opinion on these claims.
I have a question. What do you think is the right approach to adding capability for understanding similes, metaphors, and analogies into an AI system? Or is that even a right question?
No, I think that's a good question. There's many things that current systems lack that I think are really important for that kind of, reasoning. That is, one of the things is being able to kind of integrate perception and cognition rather in a way that we have a kind of more dynamic approach. So most neural networks that we have right now are wholly feed forward or mostly feed forward. Some of them have some recurrence, but we don't have the kind of integration between top down and bottom up processing that we see in the brain. And I think to perceive analogies and metaphors and so on, there's a lot of interaction between sort of seeing a current situation and having it remind you of some other situation and being able to make links between those two that involves both sort of a lot of interaction between more perceptual and more cognitive processes and also more dynamics.
Do you think that's just a higher level of pattern recognition?
Pattern recognition, excuse me, pattern recognition is a very broad category. So I would say, yeah, I mean, I would say pattern recognition is almost everything about intelligence. So yes, it is a higher level of pattern recognition.
Thank you.
If I may ask a question. First, beautiful talk. Thank you. I really enjoyed it.
Thank you.
So then a question and then perhaps a comment based on your answer. So I have slightly vested interest in it. So what would you suggest? So clearly quantity is not going to solve the hard problems of AI. And what do you think we should be doing? What qualitative changes should come about that will make it better? Do you have any guesses or hints?
So I agree with you about quantity, but I don't think it's clear to anyone that that's not going to solve the problems. There's a lot of people who believe that just scaling these kinds of approaches that we have now, we're going to suddenly get systems that or can do all these things, right? So it's not obvious to everyone.
But let's say we agree between us.
Yeah.
And I can give you an example, let's say a fly brain, which is, very much smaller than even a small brain region of human, can do many of these things, can catch a distractor, avoid a human being. So quantity is clearly not really the really major hurdle here. So what then is missing in your opinion that we should be thinking of?
Yeah, so I'm very much in favor of looking at natural intelligence and trying to figure out what properties are essential in natural intelligence. And it may be that some kind of real interaction with the world is necessary for learning in a robust way. These systems learn statistically. I showed the picture of the brain in the vat. They're doing getting these inputs and doing high level statistical correlations, but they're not really forming what we might call concepts. That is the kinds of rich associations that we learn as children, as babies, that we can use to apply to new situations. And even perhaps a fly can do that in its own world better than AI systems. So yeah, I think there's a lot to learn from neuroscience and from developmental psychology in particular about learning and how it interacts with bodies and environments.
So I give you my little vested interest part. So the common element in these networks, whether recurrent neural network or feed forward, is a threshold nonlinear unit that sums up input and generates a binary output. Neurons are not like that. We used to think neurons are like that, but neurons are actually not like that. And then there are gigantic processes and so on. So do you think that there may be something to that, the fact that neurons are highly complex entities and that threshold nonlinear approximation of neurons, maybe that's where we are missing the boat potentially?
That's very likely one of the places. And it's not just neurons, right? It's dendrites and synapses and so on, much more complex than these models. And there's other cells in the brain too. And, it's a very complex system. And, we don't yet understand sort of what aspects of the complexity of it are.
Right.
Why is that just an accident of history, or is that actually really essential?
Thank you.
There's a question in the chat. Thomas asking, do you think we should pursue human-like intelligence, or is there value in keeping AI systems narrow?
Yeah, that's always a difficult question. Clearly, I mean, there's certainly a lot of dangers in building our own human-like intelligences. We've already seen dangers with just the narrow AI that we have, in that it can be biased. It can kind of magnify biases that were in its data. It can be used to be more autonomous than it should be. All of those current problems that we have. But, there's another question, which is like, can we get AI systems to do some of the tasks that we want, like say self-driving, without mimicking human intelligence? Or is it going to lack the kinds of common sense that it needs to deal with the situations that driving, presents to us? And so I think we don't really understand enough about our own intelligence to know what tasks kind of require a human-like intelligence and which tasks can be done in a different way. So I think that's still an open problem.
Gordon raised his hand, so please, Gordon, go on.
Yeah, hi. So very enjoyable talk. Thank you. I have one way in which I snapshot the general the general knowledge question, and that is artificial intelligence may be really easy. It's artificial stupidity that's hard. And being able to get any system to express really the basic biological elements of behavior is the real challenge. What I'd like to comment on though is whether or not it's fair to think of intelligence as an entity that we can actually use as a noun, as there is one thing called intelligence. I've often thought that when I'm trying to describe this characteristic called intelligence, I cannot do it without reducing it to a system wherein I want to apply it. Once I throw intelligence into a system which has behavioral characteristics, it becomes an adjective. So we have an intelligent system, and that intelligent system behaves in particular self-preserving ways, and we can start talking about reduction of entropy within a system that results in prolongation. But that whenever I try to extract that into one substance called intelligence, I run into troubles. Love your comment.
Yeah, I think intelligence is one of those words that is less, you know, I think Marvin Minsky called these suitcase words. You know, they're suitcases full of all kinds of meanings, and they mean different things in different contexts. It's like a placeholder for something else. It's a placeholder for something that we don't understand, just like, you know, dark matter or dark energy. It's a placeholder for something we totally don't understand, and we don't yet have figured out the right vocabulary to talk about it. So it's I agree with you. It's not a thing. It's probably better as an adjective, and we may have to refine even those adjectives. You know, if you start talking about, you know, you're an intelligent, you know, I don't know, everything just described now as like, you know, smart refrigerator or things like that. It doesn't really mean anything anymore.
I have a question for Melanie. Hey, this is Taryn. Good to see you here again.
Hi.
Hey. So completely agree, of course, with your talk and all the premises there. But I also just wanted to, play devil's advocate a little bit and just kind of hear your thoughts on this particular point, Melanie, regarding this this notion of, quote unquote, big data that we can train, like this is what's happening with DALL-E, and this is what's happening with GPT 3 and 4 and all these. I wanted to ask you, like, very particularly that I definitely agree with you that I don't think that's the right way forward in order to get sort of something more general. I think the interaction is the way to go. I think it can bypass a lot of this. But what might you say in particular to folks who do believe that big passive data, such as these ultra large language models, such as the DALL-Es and so on and so forth, what might you say to them as far as why it won't work, right? And again, I definitely agree with where you're coming from, but I wanted to, but I was curious if you had like some articulation of why we believe this might not work.
Well, okay. So they do work for some things, right? They have their domains in which they work. But I guess the question is, do they actually have any internal model of meaning of the data that they deal with that would allow them to, move past their training data and be able to extrapolate in some way? And I think that's still, I don't think they do. I don't think you can get that from just this kind of, self-supervised learning without lots of prior knowledge and the kind of architecture you need for these internal models. But, that's the question. And I think that we all have to understand better how to probe these models to show that. And I don't think we figured out the right evaluation methods to do that. So
Yeah,
I'm,
great,
you know,
great.
I'm not going to
Yeah.
convince anybody. It has to be done, you know, empirically.
That's right. Definitely with you on that one. And that's definitely what we need to do for sure. Thank you. Great talk.
Thanks.
Speaking of training data, Matt has a questions on the chat. Like, so if someone said that they had some AI system that they thought had common sense, what data set would you use to test it, and what data could be used to train it?
Well, okay, so what data could be used to train it? Well, how do we learn common
Test
sense?
it, yeah,
I mean, to test it, yes. So
train.
yeah, so I think we have, so there's been a lot of, I don't know the answer to that question, but there's been a lot of proposals for testing common sense using language. You know, there's sort of the famous Winograd schemas, which were these pairs of sentences with like you pour the liquid into the glass. You pour from the bottle into the glass until it's full, and you ask, what does it refer to? Okay, and so these different common sense questions, and it turns out that a language model can answer those questions without knowing what a bottle or glass is in any deep way, just because of statistical correlations between, you know, words or phrases in the language it's been trained on. So these language-based common sense evaluations have, you know, there's a lot of difficult issues in figuring out how to interpret them. So I would be more in favor of a more abstract, idealized common sense test. I like the, if you've heard of the abstraction and reasoning corpus by Francois Chollet, that's one that I like. And it's interesting because it's, you know, it requires completely almost zero shot learning to solve the problems. But I don't know what the right data set is. And I think that's something that the community has to grapple with.
Because one of the, every once in a while when I think about this, I think of, you know, one, you're trying to get to have common sense, it's well outside of training data set performance. So I haven't looked too deeply into it, but I was always wondering, it's like, can I train a model to play a bunch of Atari games and then test it on Atari games that it hasn't seen before? Like that might be a good test to see, yes, you have learned generalization things. I can't fool you by making the paddle lower or higher. You've hit on something more fundamental.
Yeah, I think, you know, even just giving it another random Atari game to play on, there might be some, you know, way that it could, you know, use what its knowledge to play at that. But I think we have to develop sort of systematic tests of generalization and of common sense that try and explicitly test for certain aspects of it. You know, like, you know, if you raise the paddle on the breakout game and all of these kinds of sort of more systematic tests of generalization.
Thank you. Gary was raising his hand. Please go on, Gary.
Hi, Melanie. Long time no see.
Yeah.
I heard you say something about self-supervised learning, but it not being enough, I think you want to modify that a little bit, right? So babies, clearly we don't go in and set teaching signals for their neurons, right? So some sort of self-supervised learning, I think, combined with reinforcement learning and having a body. I mean, the baby sits there going like this and they say, oh, when I do this, my hand moves, right? So they learn about the world by interacting with it. And I think that's one of the things that's really missing. And, you know, I totally agree with you that for intelligence to work, it's got to be embodied. Yeah, so I don't have much, it's more of a comment than anything else, but I really enjoyed the talk. Thanks.
Thanks. By self-supervised learning, I meant like in the current language models we have, where the learning means like mask out part of a sentence and then have the system predict that.
Yeah.
That's very different from what babies do.
Well, not completely. I mean, I think prediction is what a lot of what we do. You know, if I say I like my coffee with cream and dog, you notice that there's something you didn't predict there. And bunch of people at MIT, you may know, recently showed that if you want to predict fMRI activations when people are reading a story or whatever, the system that fit the best in terms of the predictable variance was GPT-2. And BERT and these other large language models that do masked learning don't fit it as well as a system that's just learning to predict. And I think that's a lot of what we do in self-supervised learning, that fits, to my mind, very well with what we do every day, right? We walk along and we expect that when we put our foot down, the sidewalk's going to hold us up. We're not like Virginia Woolf expecting the world to swallow us up at any moment. So I think, prediction is really important.
Yeah, I mean, I agree. Prediction is really important, but also we're not just passive learners, sort of letting the world come in and trying to predict parts of it. We're very active in choosing what we want to.
Yeah, and a lot of the artificial curiosity stuff is about, when your predictions aren't matched, that's when you start paying attention, right? And I guess the other comment I'd make is, it seems to me one of the really important things that's missing in all these systems is memory, right? I mean, if GPT-3 had a memory for all the conversations it had, it might, look at the difference between like the neural Turing machine versus just a standard LSTM network. With a memory that it can use, it generalizes well to examples that it hasn't seen before. And having a memory, I think, is another really important factor that we're not taking into account in these large systems.
Yeah.
Long-term memory and short-term memory, both.
Another reason to integrate cognitive science back into AI.
Yeah. Well, yeah. I like. I always think of myself as a cognitive scientist collecting a computer science salary, which is the right way to do that. You don't want to do it the other way around. Yeah.
So we have a question about physics, like does adding physics knowledge to AI system is a step in the direction on common sense, do you think? Just kind of on the chat.
Yeah, absolutely. I mean, obviously, part of common sense is our so-called intuitive physics. And so being able to know what's going to happen, if you set your coffee cup down on a table, it's not going to fall through. That's obviously important, that kind of thing. Josh Tenenbaum at MIT talks about intelligence sort of being this what he calls the game engine in your head, which is like a physics engine that you're using to simulate intuitive physics in the way you would in, say, a video game. So I don't know if that's what intelligence is, but it's certainly being able to do that's a big part of our reasoning.
Definitely.
We have a quote from Einstein posted by Josh Eldon that said that common sense is nothing more than a deposit of prejudices laid down in the mind before you reach 18.
Mhm.
Tell that to the Department of Defense.
So if no one has a questions, I will ask one. So in all those models you were showing, like it seems a lot of people like in the optimistic side were hoping for like bigger models, like more connections, more computing power and those kind of things. I was wondering, so it seems like they're like kind of advocating for like more complexity, basically, like in a way, like to get to intelligence. And I was wondering if there are other researchers in especially in the AI fields that are like looking at also like the kind of constraints, because having like all the computing power and like just burning like gigawatt of power to do like those kind of things while the brain is not using that much kind of energy, like is there like a way of like constraining also some of the systems to and still retain some of the intelligence of it?
Yeah, someone described what Google's doing is destroying a rainforest in order to explain a joke. But yeah, obviously, you know, that we don't require that much energy. Although it's hard to, you know, it's a little bit hard to compare. We spent, you know, as someone said, 18 years learning common sense. But yeah, there's a lot of work on how to make these networks more energy efficient and more less dependent on huge corpuses of training data. But that's a big area of research in AI. But it's obviously it's easier if you're a big company to just scale up, as you have infinite money, so you can just scale up, and these things then, you know, can do more fancy things.
Yeah, for sure. But I think where I'm going is is there like on top of adding a body, like is there like maybe some constraints in terms of the kind of hardware or like the kind of platforms we're using to run those models that might play a role in terms of intelligence, not common sense, just intelligence? Do you think that's the right kind of hardware?
Yeah, I mean, you know, if we're constrained ourselves, like, you know, I don't have the kind of supercomputing powers that a big company does, but that may mean that I'm spending more time thinking about kind of deeper principles of intelligence than just scaling giant neural networks. But I'm not sure if that's what you're asking.
Then I was just wondering if AI people were like more into those kind of thinking in terms of complexity, because complexity is one thing. Like I think it's like a good arguments. Like the more complex the systems are, maybe the things we're missing. Like Mayank before that was mentioning that the activation function was perhaps like
right.
simplistic. So maybe adding more complexity like to the model might just like
right
lead, like better things. But like, is it just like there's like some limit to the complexity, I guess we can add.
Well, for instance, if you add, say, much more feedback, which is important in complex systems, maybe that's really important in the brain, but we don't know how to do that correctly in AI systems and in deep neural networks. That's making them, you know, harder to control, harder to train. All of these kinds of things mean that you have to come up with new algorithms for learning and inference and so on, which are completely different than the ones that have already been figured out, like backpropagation.
I think you may have hit it on the head there, picking up on what you and Gary both were saying about embodiment. When human intelligence or animal intelligence evolved in the wild, it was in a body, trying to avoid predators and becoming a prey, or being a predator and trying to catch a prey. And so there was this constant back and forth of feedback and anticipation in a very dynamic, moving environment. And most AI systems grew out of a static environment where there's a face to recognize or a scene to analyze. And the newer language models are using some sense anticipation to figure out where the sentence is going, to figure out the meaning. Self-driving cars are trying to do something similar, moving towards a more dynamic way of interacting with the world, but they're coming from a different place and way behind as far as getting to this embodied approach to things and prediction, like Gary was talking about.
Yeah, no, I agree.
Any more questions or comment? Anyone?
Yeah, I have one comment. I just want to say this was an amazing talk. Thank you so much for providing the talk. And my question was, natural intelligence has had time to evolve and learn and have interaction with this environment, whatever domain that it is. I'm wondering whether we have to do something similar where we have to learn some policies or some architecture that allows us to actually learn common sense, such as you mentioned, Matt talked about what type of training data we could use to do that and to first train it and also evaluate it. I think those are some of the questions that we're really trying to ask.
I'm sorry, I had trouble hearing that.
Just following up on Matt's question, how do we train a generalized model or even a modular model, which I think Meta has come up with a white paper saying, perhaps if we learn on the external model and an internal model of the world, how do we train such a model to have this, to have common sense or to generalize?
How do we train? Well, that's certainly a billion-dollar question. Right. Nobody knows the answer to that. So the question is, do you need something that's embodied in the world? Do you need just more data? Do you need some kind of teacher that's actively interacting with the student? And do you need some kind of curriculum? People talk about curriculum learning, where you've kind of staged learning in certain ways. But I think nobody knows how to do that to get to like common sense. So that's the big question.
Do you think that you will
I wanted to
require,
also ask Melanie, it's Taryn again, just along the same vein with
your audio is a little bit weird.
Taryn, I'm sorry, I couldn't hear you.
It seems the connection dropped off. He's on the phone. I'll wait for him. I was wondering, do you think that maybe like having like learning, like the learning phase, like far longer than what we have now, like might be something that maybe necessary for like learning those kind of essential concepts? Like it seems to remind like there was like some robots like in MIT that were trying to learn like very simple things like pushing a cart and trying to understand that, but it was like kind of learning like transferring those kind of knowledge incrementally, like on a very long time scale. Do you think that it's something that people are like pursuing now, like those kind of?
Yeah, there's kind of a buzzword of lifelong learning or continual learning, which is trying to get at that, to have a system that's not just, we train it and then we evaluate it, but actually it's just constantly learning. But then how do you get a system like that to work without sort of forgetting important things that it already learned? So there's some challenges there.
It's a question for Melanie. This is Taryn again. Sorry, I think I got disconnected. Along the same questions around compute resources, how might, if you did in fact have the compute resources the big companies might have, and sorry, I'm sitting outside, how might you imagine those compute resources be better leveraged towards the paradigms that we're talking about here? Right. So if you wave a magic wand and you have access to the gazillion GPUs or whatnot that you might have at Google's or Facebook's, what might you do differently there? It's not a trick question. I'm super curious.
Yeah. Yeah, I'm not sure that having that many GPUs is going to be the key to figuring out these issues. So I think you have to, rather than just going whole hog on big data and big compute, I think to look more carefully at what are some of the important principles of natural intelligence, and to try and think about how those things could be implemented in AI. So, I like the idea of virtual environments for AI as opposed to sort of just, like static data sets. So I'm a big fan of some of these new approaches where people are building these virtual environments. There's one that I like, a really simple one called the Animal AI Olympics, which is based on experiments from animal intelligence and is trying to simulate those experiments on a reinforcement learning agent. So I kind of like that idea of using kind of a virtual reality approach, which I guess you need a lot of compute power for. But I also think you have to do a lot more thinking about principles than just the kind of throw huge amounts of data at it. So
to paraphrase that, turn off that system and take the money you save in electricity and hire a bunch of cognitive scientists.
Perhaps. Perhaps. Listen, unfortunately, I have to go to another meeting now. But I've really enjoyed this discussion. It's been great.
But thank you for letting some time for discussion. Actually, it was really nice. Very nice talk again.
Thanks.
Yeah.
Great
Thanks a
job.
lot.
Thank you.
Really
Thank you.
appreciate it.
Thanks a lot.
Very much. Bye-bye.
Bye-bye.
Bye.